Swayam Prabha. Digital India. Educated India.
I'm going to quickly explain slightly later about this mean. Okay, this is wave, right? Wave is surface wave. On the surface, let us say 1 meter of wave amplitude or 2 meters of wave amplitude. And you just imagine that way. With it going on in deep water, such kind of amplitude will decrease. How quick it decrease? The two numbers shows that. Lambda is wavelength. Right? You go to wavelength this much, you go to quarter wavelength, the water particle speed already decreased to 23%. Right? If half wavelength, it decreased to 5%. Right? So that is for the deep water. Okay. For shallow water, it's different. Shallow water, you can say. And later, when we say the particle motion, you get better sense about the how much it decrease. Okay. So let us resume the discussion, and now we already get the velocity field and horizontal velocity, how quick it decrease, right? For shallow water, horizontal velocity didn't decrease same, and vertical velocity and for the shallow water decrease linearly, and for the deep water exponentially. Okay, let me say that way. This is Kz. Did some student ask me, okay, wow, Kz should become larger and larger, because you will think Kz, right, exponentially larger, right? Why we say decrease? Z is negative, right? So you just imagine that way. This is coordinate, right? This is Z, and upper side is positive, this side negative. This is decrease. Okay, so let us continue. This is velocity field. Next is the pressure, right? And the pressure here, you care about the dynamic pressure, not the static pressure, right? And so you use the Bologna equation if you already get the velocity field. So I just gave that, so I gave you a conclusion. Okay, so for shallow water like that, the pressure is linear decrease, right? For deep water, it's not a linear relationship. And also, you get a sense what we care about the dynamic pressure. Dynamic pressure and the follow same pattern as what we learned just now. And what I mean, if the water get a quarter of wavelength, the pressure already decreased to 23%, to 23%. Therefore, you just imagine that way. Some company like Carnegie Wave in Australia, right? They develop wave energy converter submerge into the water, and actually for military application, you don't want anything outside the surface, right? You submerge into the water. This cannot be too deep. If you get too deep, the pressure, like that, dynamic pressure, decrease too quick, right? So it's the same pattern, E, K, Z, right? So, and therefore, you try to keep as close as possible to the surface, but make merge into the water. This is pressure field. So, a third is particle orbits. Particle orbits, that is what I mean, the particle motion. At the beginning, you see the figure that I show, that's particle motion. Okay, so, and how to understand the particle orbits? You know the surface wave amplitude, A cosine kx minus omega t, right? And K wave number cycle per length. Omega cycle per second, right? So the potential velocity potential function, you can get that. Based on that, you can get velocity at each points, right? And there's some approximation to say, and this velocity is the mean velocity and also the velocity amplitude, right? So this velocity amplitude eventually if you go through some mathematical exercise, I give you conclusion directly, it takes this form. And what does it mean? So if you look at this A amplitude, right, this is A, x direction, and B is another direction, amplitude. So such kind of sense to show the particle motion. Particle motion means, look like this circle, right? It will be the motion around this. The amplitude is x direction is A, y direction is B, and A and B follow this function, right? And this function, if you have sine, cosine like that, okay, and if you say the shallow water what's look like that way, shallow water A direction, right, and KH means very shallow water is small, right, eventually, and A dimension wouldn't change, and okay, B dimension wouldn't change, also not A, okay, with the A dimension, okay, and the B is the water dimension, right? The amplitude quickly decreased. So in the shallow water, the particle motion like that way, okay, and on the surface is large amplitude in x direction, z direction, right? With when the water get deeper and deeper, and then the x dimension didn't decrease, but z dimension, the particle motion decreased. Okay, so then the deep water, and the deep water everything look like one circle. Okay, so here you can have A and B, and KH is large. You find A and B will be constant. Okay, in that way, and A and B is the same, and with the Z decrease, the amplitude decrease. Okay. So, and in the deep water, and the water particle more like a round circle, right? Round circle, the amplitude decrease with the depth decrease. So that is what the mean. Okay, when we say 5%, 23% means, okay, this particle motion, and at the surface, let us say the circle area, this amplitude is 1. At quarter wavelength, this amplitude decrease to 0.2523, and if at half wavelength, and this amplitude decrease to 0.05, right? This say the surface will quickly decrease. However, in the shallow water is different. Shallow water you still have horizontal dimension. So look at this one. If you design some wave energy converter, right, you for the shallow water to work, and you probably want to make use of horizontal motion. For example, you have surge wave device, right? Take advantage this surge motion, because the surge motion amplitude didn't decrease, right? And if you want to put this in the try to use a heavy motion point absorber, you put in the deep water, right? Surge wave device is good for the shallow water, right? Make sense? Right? Shallow water, you make use of horizontal motion, and the deep water here you can use vertical motion. Okay, most case in between. So let us take a look at this figure. Okay, this is if you put a particle like here, you can say how the particle motion. So you want to say, well, what's wrong, right? This look like a professor. You tell me this particle is a closed loop, right? But now this figure shows the particle is not a closed loop. What's wrong? It's moving. Why? But ideally, this equation shows the closed loop motion. So this linear wave theory. If you follow this linear wave theory, there are not all approximation, right? For example, the wave amplitude compared with the water depth is small, right? And also the wave amplitude compare with the wavelength, okay, is small. Okay, so small wave theory at the beginning, and when we start, let me go back to here. Let me come here, okay. And small wave, right? Small wave means the wave amplitude and wavelength comparison. Wave amplitude is much smaller than the wavelength. Okay, so in such kind of case, you can have the closed loop circle. Okay, and otherwise there's some motion. Okay, you can say this. Right, you get a sense the particle didn't come back exactly. Okay. So, and we are going to see some functions. Okay, one is linear superposition, right? And you have wave go the different direction, and the wave frequencies are the same, and the water depth is the same, then K will be the same, right? And now the two waves, you add them together, and you go through mathematical equation, you get this very interesting phenomenon. This water wave, eta water wave amplitude, is a function of cosine omega t times cosine kx. What this means, for fixed point, any fixed point x, okay, then the amplitude just cosine, the move up and down, right? And then the amplitude of at fixed point, right, it depends on kx0 exactly location, right? So this amplitude is fixed, right? If you have fixed time, okay, and this one look like this shape, okay, that is called a standing wave. And standing wave, and there's some video here, and let me say click to see it works or not. This is YouTube, and some video shows the standing wave. So you get a sense, right? If you have any time, any fixed time, that's look like sinusoid in the space domain, right? You fix any point here, you will see wave move up and down, and this is standing wave, right? So, and the standing wave, you have wave transmit in two directions, same frequency, you get this result. And okay, and let me come back, okay. Okay, that is the concept of standing wave, okay. And standing wave can, the amplitude, wave amplitude can, let me see that, okay, doubled. So, and one way to generate a standing wave is you have hardwire the reflection, and in such kind of reflection you can, so, and in that case you have hardwire, and then you get standing wave, right? This standing wave can be dangerous, especially if the amplitude become larger, right? And you have hardwire like that, reflection can happen standing wave. Another way to can create a standing wave, you just imagine that way in your tank. If you have two wave makers, right? You make the wave out of phase like that, you generate a standing wave. Okay. So another thing we need to understand what mean wave group, and here, and so, and there's another YouTube to see the beat phenomenon. I skip that one and directly go to the beat. Okay, basically you have wave omega frequency and wave number k, right? And now this wave number changes slightly, and the frequency changes slightly. Now you have two waves, right? And this wave to add together, and so then add together, you use mathematical equation, it becomes this form, right? So, and what's look like? Okay, here this original wave kx minus omega t, right? And then the amplitude will be the envelope, and you draw this wave amplitude is more like that way, and this is called beating, right? And we have this is beating, and let me show, before I introduce the so-called group velocity, I want to show you some video first. So this is, I say this is phase velocity, right? And now you have two waves, and these two waves, the wave number changes slightly, the wave amplitude changes slightly. This you know what's the combined look like. Okay, the combined, there's where envelope is moving, right? And also you can say any points, and for example take a look at the red dots. Okay, and let us show this again at the beginning. Okay, pay attention to 2 points. One is the black dots and another red dot. Black dot shows the envelope's motion, and the red dot shows one particle, the move up and down. Okay, and take a look at here. The red dots that shows the envelope moving, right? And take a look at another look at the red, right? The amplitude, and the red, this points the moving speed, that is called phase velocity, and the black dots, the envelope motion, that is called group velocity. So, and group will we already learned the phase velocity, right? Phase velocity omega divided by k, and we learned that in deep water was the phase velocity, and the shallow water was the phase velocity. They are different. And now the group velocity is the envelope here, right? This envelope's motion. Envelope's motion, the velocity should be delta omega, right? Small delta, right? Divided by delta k, and if delta is small enough, is dw dk, right? So that is the group velocity. So this already gave the sense the group velocity and the phase velocity are different. This figure shows the red dots move faster than the black. That means the group velocity is smaller than the phase velocity. Okay, so these two, group velocity and phase velocities, are different. Okay, so let me say that way. So already show that there's an envelope, and in this envelope, and there's water move up and down, right? One is group, another is phase. Okay, and if you have the water, if you have different water depths, the two are different. And for deep water, and the group velocity is half of the phase velocity. Okay, and for the shallow water, group velocity and phase velocity are the same. Okay, and let me say that way. And for the deep water, this is usually we say, right? You have long wave amplitude, and long wave amplitude, therefore lambda is larger, then long wave will transfer faster, right? And then if you have short wave, translate slower. No matter what, there's envelope. You have such kind of envelope, then the group velocity transmit is half of the phase velocity, right? Shallow water, they are the same. So intermediate is just in between. Okay, now it's time to talk about wave energy, right? And what's the energy in the wave, right? Wave energy conversion, this is mostly important. How much energy is there, right? This wave energy. So this part shows the definition of wave energy. And so we just take one period in the water, right? So to say how much energy will be there. Okay, and what kind of energy will be there? What do you think? This will move up and down. What kind of energy? Kinetic energy is particle motion, there's velocity, right? And there will be also potential energy, right? The gravity, right? So the energies are two parts, and kinetic energy and potential energy. Where's the potential energy, right? Potential energy, you just think that way, they will move up and down, and at a certain amplitude on the surface A, under the surface amplitude decrease, right? Keep in mind. And then the potential energy, right, is rho gh, the integration. Rho gh integration with potential energy, there's one is the rho gh integration is when there's no wave, still water, right? On the other side, there's water, and then this your integration, you will find that is very interesting. The 1 over rho Ga square, this A is amplitude, is in one wave period how much energy, potential energy will be there. Okay, and similarly, and if you look into the particle motion, that U square plus W square, the total velocity, you integrate in this particular volume and wavelength, okay, and you will find this also 1 over rho U A square. Okay, this is kinetic energy and potential energy. You add them together, this is total energy, 1 over 2 rho Ga square. Okay, so as you can see, the wave energy in one period, okay, is very simple relationship, 1 over 2 rho Ga square. So keep in mind that energy is one wave length, this much, right? So this is why you will say, oh, where's omega, where omega? So this is just a one wave period. Okay, so as we say, this wave is transmission, is moving, right? And there are two velocity, one is group velocity, another is phase velocity. We would like to say how much energy goes through one particular line. For example, this wave front, this for this water depth through the surface to all the depths, to say how much energy transfer goes through this, right? This is called energy flux. That is the most important part. Energy will transmit. Okay, so energy transmit, that means total energy over one period, one wavelength, okay, 1 over rho Ga square, and actually the energy transmit at the speed of the group velocity. Such kind of thing you can get a closed form solution. So that is here, this energy flux transmit at the group velocity, and you can get a closed form solution. I skip this how you get this solution, but I gave you the conclusion. So energy transfer at the group velocity across this surface area. So if you have deep water, and this can be even further simplified, that is amplitude, omega, or period, and so this wave height relationship. So I want to put some number in your mind to say how large this one. For example, you have 6 seconds wave 1 meter. This is mostly like an Indian surrounding the Indian's water, right? This wave flux density is 5.7 kilowatts per meter. What does that mean? Okay, the wave transmit here and 1 meter of wave front width. Okay, and the wave transfer energy is 5.7 kilowatts. You put a 1 meter device there in the water, right? And it will come to you. If you collect all the energy in 1 meter of this width, is 5.7 kilowatts. So 5.7 kilowatts is a lot. So for example, you use your cell phone, you know how many watts? 25? No, cell phone is much less than that. Cell phone is about 1 watt, right? The laptop, and usually that laptop adapter is 60 or 40 watts, right? In home, usually average the power to power home, you need different country are different, right? US waste or not energy, probably each home the average is about 1 kilowatts, right? So if you get like a 5.7 kilowatts, you get 20% of energy you can power one home, right? This is just Indian Ocean surrounding this Indian, right? And like U.S. East Coast, for example, like New Jersey, like Virginia, right? And typical wave is 1.5 meter and 8 seconds. You plug this relationship here, you'll find the wave energy flux is 17 kilowatts per meter. So this is huge, right? In West Coast, like California, like Oregon, such kind of water can be 10 meters wave amplitude and 10 seconds wave, and this is about 40 kilowatts per meter. So it's huge, right? This is why wave energy conversion, this technology is very exciting, right? So if you build one device, if you can get all the energy or 20% energy, is huge, right? And where solar, 1 square meter solar in the sunlight is 1.5 kilowatts per square meter, right? And this sun usually solar you can average 6 hours, right? And if you can get 200 watts, you times 6 divided by 24, it will become how much, right? 50 or 40 kilowatts average. Here you get a small device, this 10 times more. Okay, so this is good, but also bad, right? And the energy too large. As a result, all this system you have to survive in such kind of large wave input, especially when storm happens that can be significantly high. It faces another challenge in how to design the wave capture device so that the system can survive in storm condition, right? So, okay, and let us say another figure I want to show. This figure shows the wave power flux density around the world, different color, right? And it's South American. This you can say is 60 kilowatts per meter, right? And in this Alaska, right? The California here, and in this region, you can get 40 kilowatts per meter, and U.S. East Coast, you can get 15-20 kilowatts per meter. In Great Lakes, right, less than 5 kilowatts per meter. And here you can get the sense in this region, right, is 5, right, is even 5 kilowatts per meter. That is energy still significantly better than the solar, right? You will get energy. So in this region, you can get 10 kilowatts per meter. Okay, so the research in the worldwide, and for example, in South Korea, right, they build a wave energy converter that is similar density, energy flux density as the water here. And last year, I traveled to Spain in this area, and you can say this is 15 kilowatts per meter in this region. They built a wave energy converter station using alternating water column. China here in Guangzhou Energy Institute, and it's near Hong Kong, and this place. Okay, they build a wave energy converter, and they also test in this region. The region is pretty small, it's 5 to 10 kilowatts per meter. And they build a 1 megawatt wave energy converter, and they test in the water. It has been there for more than half year average. They produce more than 300 kilowatts. And the technology is there are two good things about the technology. One is the modular design, and each module is 60 kilowatts. They replicate different module. Another thing is they have very smart design about wave capture structure. They called sharp eagle. When we talk about PTO, I will mention that again. Okay, so in United States, the build Pecco site is in this region. In Oregon State, they already spent more than $100 million to build the wave test site, and it's in a water of depth 70 meter, and the wave flux is 40 kilowatts per meter. Here, Hawaii, there's a functional test site, wave energy test site WEC. Okay, the average wave energy flux density is 14 kilowatts per meter, and there are two sites. One is 30 meter depth, another 80 meter depth. Lake Michigan, right, the energy flux is 2 to 3 kilowatts per meter. The wave period is 3 to 5 kilowatts. And another place in North Carolina side, there's a test site. There's one is 5 meter, another even 11 meters. This depth is always changing. The reason is the sand environment, the wave settlement brings sense. So sometimes you see some document 11 meters, 10 meters, 12 meters. The flux and is about 6 kilowatts per meter. Okay, so that is I list these three. That is test site. Sometime you can read the papers. People did the test in this site. Okay.